Good morning, students. Mr. Carver here. This is 4.4 continued. This is the second fundamental theorem of calculus. It's the last of about 5 theorems that are listed in this section. The second fundamental theorem is really just a shortcut, and let me just kind of explain how this works. So let's start off with an integral, and we're going to go from 1 to x. So they're going to use a variable upper bound, and we'll do something like the cosine of t dt. They're using t's here to separate, or to differentiate rather, the interval of the variable of integration from the variable that distinguishes the interval. Now what we're going to do is we're going to integrate this function here, cosine of t dt, from 1 to x, and then what we're going to do is we're going to derive that expression with respect to x. So again, they're just using x's and t's just to make this a little clearer and more obvious as to what's happening. So check this out. Let's start with the inside first, right? If I were to actually work through this, this is really the area from 1 to a variable value of x. So I anti-derive the cosine. That gives me the sine of t. That gives me the sine of t evaluated from 1 to x. And then, of course, at some point, I'm going to derive this with respect to x. According to the first fundamental theorem of calculus, I take the upper bound x and I plug it in. So inside here, I've got the sine of x minus then the sine of 1, which is the antiderivative evaluated at the lower bound. And what I'm going to do then, after I figure that out, I'm going to derive that with respect to x. So let's do that now, since I can't combine those. All right, I take the sine of x, rather, and I derive that. That gives me the cosine of x. And then I take the derivative of the sine of 1. Now, the sine of 1 is just a constant. I don't know what that is. Use your graphing calculator for it, sine of 1 radian. So when you derive that, it does go to 0. This, then, is your answer. So I've integrated it, evaluated it, and then derived it with respect to x. And it really puts me back to where I was before. And that's the shortcut, basically. So the cosine of t goes to the cosine of x. Now, unstated in this is it's actually multiplied by 1, which is the derivative of the upper bound. And that's really how you do this process. You take this original function right here. You plug in any variable value for an interval. So I took this x and plugged it in. And then I follow it up with the derivative of that bound. Now, to be completely consistent, what I could have done is I could have taken the upper bound and plugged it in, followed it up with its derivative, and then taken the lower bound and followed it up with its derivative as well, and I ended up in the same spot, right? This ends up going away. All right, so let's do another example here. Now, a giveaway that indicates we will be using the second fundamental theorem is basically exactly what you're looking at here. You're going to have 2 separate variables. You'll have a variable bound either on the upper or lower end, and you'll have a different variable inside. In this case, it's t. It's most commonly t. And so instead of going through this entire process where we anti-derive, evaluate, and then derive, let's just jump straight to the answer. So again, what you do is you take the upper bound, which is variable, and you plug that in. That's x squared squared plus 2 times x squared minus 4. And then I'm going to follow all of that with the derivative of that bound, and that's 2x. Now, at this stage in the game, you don't understand why I need the 2x afterward. When we get into the next section, section 4.5, you'll see this more clearly as we begin to anti-derive chain rule and product rule, all that good stuff. But for right now, you're going to have to take my word for it. This, then, is your answer. Now, the reason this is my answer is because if I did it again with the lower bound, by plugging 1 in for every single one of my t's, I'd follow that up with 0, which would eliminate completely that second expression. By the way, this may be cleaned up slightly in the solutions manual. That's x to the 4th plus 2x squared minus 4 all times 2x, and then they could distribute that out. That's 2x to the 5th plus 4x cubed minus 8x. All right, let me change it up just slightly. Let's do something similar to it. Let's derive with respect to x, the integral. Let's do x squared, x cubed, And let's do the tangent of t dt. All right, and again, rather than integrating this, and by the way, you don't even know how to integrate the tangent of t yet, not taught it to you, we're just going to use the second fundamental theorem shortcut. So what I do is I take the tangent, I replace it with the first upper bound, and I have to do that because it's a variable. This is x cubed. I'm going to multiply that by the derivative of that upper bound. That's 3x squared. Now, according to the first fundamental theorem, remember I have to subtract. Since this is now a variable instead of a constant, I need to use the same technique on the lower limit. So this is going to be the tangent of x squared, and then I follow that up, of course, with the derivative rather of the lower limit, and this then is my answer. So that's the expression that you're going to get if in fact you actually did integrate it, evaluate it, and then derive it. All right, I think that's all you need. Thanks, guys.